In one of my first programming classes in college, we had an assignment to draw the Sierpinski triangle. What happens when you write a program like this? Well, you code up some simple rules, and then you run your program to see what'll happen, and out pops this beautiful fractal pattern. But that's not all that happens. The Sierpinski gasket is like this gateway drug, and you find yourself exploring a bunch of other fractals, like this one. Whoa, how did this pattern come about? I always thought this was discovered by Benoit Mandelbrot, but it wasn't. And I even went to a public talk Mandelbrot gave when I lived in Cambridge, Massachusetts. But the fractal, known as the Mandelbrot set, was actually defined by someone else, Robert Brooks and Peter Metelsky. Later, other mathematicians developed the math around it and named the fractal in honor of Mandelbrot, who was an expert in fractals. It's interesting to see the arc of how this fractal was drawn. I'm imagining lots of research money being spent to draw some textural stars in 1978, and then I'm feeling humbled by the flashy animation running in an animated GIF in my browser. A lot of the first images were created in the 80s, and Heinz Otto Peitgen of the University of Bremen in Germany helped popularize it in an exhibition in 1986. The exhibition was put on by the Goethe Institute, an arm of the German government that promotes the German language. I've taken some of their courses, so it's fun to see them pop up in this context. And I can't help to note, his last name looks very much like how you might say almond bread in German. But anyway, this article has the formula you need to draw the set. You pick a region of the complex plane and cut it up into discrete pixels and test each pixel as a complex number. It's kind of cool that this depends on the same mathematical object that makes quantum computing possible, complex number. And I love the 1985 description that you need a, quote, reasonable number of iterations to see if you take z beyond some reasonably large number, its size depending on your patience. Over at the Computer Language Benchmarks game, the Mandelbrot set is one of the micro benchmark programs. Here's one written in Common Lisp, submitted by someone named John Smith, and I'll run it here on the benchmark size 16,000 by 16,000 pixels, and it takes jump cut, and it outputs a BPM file, and that's what you see in the background here. BPM is a really simple format. It's just pixel on or pixel off, and you know what that means. You can draw the Mandelbrot set in Google Sheets. First, I need the helpers that are going to cut up the complex plane. That is, make each cell correspond to a complex number in the range. Mandelbrot real will give the real part of a column, and Mandelbrot imaginary will give the imaginary part of a row. Next, I'll write the driver function, Mandelbrot, that gets the complex number for the cell and does the test. Finally, I'll use a recursive function to test and iterate. This code is carrying out the squaring and adding, which involves the complex number z from the recurrence and c that goes with the pixel. The base case is that we've iterated enough 50 times, or we've diverged. By returning the number of iterations, we can get a color scale. The points that diverge right away will have lower numbers, and the points diverging slower or never diverging will have higher numbers. Okay, I'll use the smaller size from the benchmarks game for testing, 200 by 200, and now let's see if it works, and also more importantly, how long it takes. Do we have sufficient patience? Okay, so that produced a bunch of numbers. Let's add conditional formatting to color it in. There it is, the Mandelbrot set. From here, some things you could try would be using different coloring or changing the output of the test. What if you pass it through the log function or did some other modification to the output? You could also try it on the range known as the Seahorse Valley, and you can look up what that range is, but that's the place where you'll find intricate and beautiful fractal patterns.